Hello everyone, Mr. John here for Airteam Institute's Introduction to Algorithms. In this video today we're going to be talking about Big O notation. So this is a little bit more of a mathematical concept, but it's really something that is used all the time when we're talking about analyzing algorithms and how effective they are, how efficient they are in terms of their performance. Continuing off the last video, we talked about the different ways we could measure kind of an algorithm's goodness. We talked about whether it's correct, how usable, easy to read is it. We talked then about the two main quantifiable methods of algorithmic complexity, and that was time complexity and space complexity. So these two things are what we're going to be kind of focused on mostly when we're talking about Big O notation, because Big O notation is going to give us the framework for measuring these things. This can be used for both, but really this is most important in terms of time complexity. That's what we're going to be doing most of our analysis with, right? Because this is where you can look at kind of the steps in the algorithm and try to determine, how to maybe make the algorithm more efficient, things like that as well. You could apply a lot of this to space complexity. We will mention it at different times. But as I've kind of been saying, one of our big focuses and a good place to start is thinking about time complexity. How long does the algorithm take to run? And really, as we mentioned before, but we'll stress today again, we're really talking about growth rate. So this is always as a function of your input size. So, we don't really care how kind of efficiently it runs on a specific value. We'll say actually a little bit more about that with one of our kind of Big O notation classes, if you like. But, we really care how this grows depending on your input, depending on what you're putting into the algorithm there. So, in terms of this Big O notation, it's probably easiest to understand this in terms of examples. And we're not going to go in too much detail in this video about official mathematical definition of this. Those things kind of are a little bit more complicated than they're worth in a lot of ways, right? In other places, we can maybe discuss those a little bit, right? Or you can do some research, but it's a pretty intuitive notation. And so I want to focus on giving us that intuitive understanding of a problem and of what this notation means and how it's used. So the easiest way, we have some kind of simple examples here, right? But the easiest way to think about these things often is in terms of names we're already comfortable with, right? So the three we have on this screen, I want us to kind of think about as linear, quadratic, and constant. So we have three of these examples here. So O of n, this would be kind of our linear class, right? Our linear growth rate here. So what we're kind of saying here is that as the size of your input, right? So remember here, let me mention that here so we have it too, that n is a measure of the input size. So how kind of big is your input? Maybe in certain cases, usually not, but if you're doing something specific, maybe n could be the number of digits your number has. More often, it's something like how long your list is. So in the next couple videos, in the next couple sessions, we're going to be learning about different sorting methods, things like that. And so that's a good example, right? How many things are you sorting? Are you sorting 10 elements, 100 elements, 1,000 elements, right? All of these things kind of give you an idea of, what the size of that input is. So if we're talking about O of n, this would include 2n plus 3, 4n minus 8, also 200,000 n plus a million, right? So all of these things here really don't depend on the constants, right? So let me give myself a little bit more room here. But one general idea here is that the constants in lower terms don't matter. So kind of general way of thinking about this is, so constants don't matter. And then we have kind of lower terms, and let me put lower in quotes here because it's not always polynomials that we're kind of talking about there either, right? But these are kind of the ways to think about this Big O notation. Approximately, if you zoom way, way out on the graph, even the 200,000 n plus a million is going to be a lot, right? So that's kind of this linear growth. And as, in changes, it's going to be kind of directly proportional. So those are kind of the things you want to think about there. How is the proportionality changing along the way? Any type of quadratic, we would consider O of n squared. So whether it's 6n squared minus 4n plus 3, n squared plus 200n plus 999, even if it was something like n squared divided by 1,000, minus 200, that would still all be O of n squared. These are all quadratic expressions. They would all have this quadratic growth rate, and that's what we kind of care about in the Big O notation. And lastly here, and this is one that's kind of worth mentioning a little bit more, we also would have constant things. If an algorithm has a set number of steps, doesn't matter how complicated it is, if it has a set number of steps, this algorithm is always going to finish in 200 steps, then it would be constant. If it's always going to finish in 5 steps, it's constant, It does not depend on the size of your kind of input. There's less loops or things involved, Even though we need to be a little careful with loops, as we'll see, If it has this set number of steps, we would kind of always say that that's a constant growth rate. Again, we talked about this a bunch in the previous video, but it's worth mentioning here again, right? Why don't these constants matter, right? Why don't we care about the lower terms? Well, these are all of those complications from last time, right? My computer versus your computer. As computing power gets faster, right? Maybe the 5 steps today take as long as 200 steps in, 2 years. So those kind of things we don't necessarily care about as much, right? It's more so, right? Can we get an understanding if we scale these algorithms to huge sizes, right? Are they going to blow up? Are they going to be feasible? Not feasible? Things like that. Because really today especially, computers are so fast that if n is small, right, pretty much any algorithm you run, no matter how horrible it is, right, is going to be fun, right? With today's computer speeds, right, if n is relatively small, any kind of growth rate is probably fine, right? So even when we see kind of horrible ones that I'm going to kind of call bad, or not necessarily bad, but right, O of n's or O of functions that we want to avoid, if you're talking about 50 or 100 in some cases, or definitely 10, 20, doesn't really matter how bad your algorithm is. You have to do right a lot of stuff wrong to make an algorithm blow up and not be feasible to run based on today's speeds. So that's really why we're kind of caring much more about how these things grow, how these things kind of go as we have higher and higher input sizes and stuff like that as well. So in terms of that, right, I do want to kind of just see some practical applications or practical ways of thinking about this, right? So one of the things we did mention briefly is you could talk about things in terms of time, right? So we could sometimes at least think about values as just how long does the program take to run. So I want to show you a little bit here how we could kind of use Python, right? We mentioned it previously, but now let's see a specific example we actually can look at, right? Timing an algorithm in this case. So in terms of a previous video, right, and kind of some discussions and things like that, one of our most basic algorithms we kind of looked at here was this sum of first n, right? So actually here, let me just kind of maybe even space this out a little bit so I can have a little bit of space to kind of work with here, right? But this was one of our algorithms here for writing out, right, what is the sum of 1 plus 2 plus 3 all the way up to plus n. So, right, if we start kind of thinking about this, and if we want to kind of analyze this kind of algorithm here, we have our definition, right? And let me come back to some kind of questions in a second. But right, first of all here, right, this is kind of one step in this case, right? We have our partial sum equals 0. That's one line of code, right? We're assigning a variable. We want to kind of consider that one step. Now, our question might be, inside our for loop, how many times does this partial sum equal partial sum plus 1, right? How many times does that run? Well, it's going to run one time for each part of the loop, right? So this is going to run kind of n times there. We have our return statement. Maybe we want to consider that as a kind of step here as well. And because these are sequential, right? First thing, then our loop runs, then our kind of return statement runs. We're going to be adding up all of these things, right? So if we want to talk about kind of a particular number of steps, right? Again, these things are problematic, right? We're not going to really worry about this in the future, right? This is n plus 2 steps we have here. And then, right, we will say that this runs in kind of O of n, right? So this is O of n, meaning this is a linear growth we have here. Now, right, the power and usefulness of the O of n stuff is that we don't need to worry so much about these details, right? So you might say here, should we count our first define statement, right? What if you want to include that as a step we have there? Well, sure, right? Then we have an n plus 3, but it's still O of n, right? So some of these details don't matter. As we mentioned before, is it as easy to do a return? Is that going to take as long as far as our computer's concerned as adding I to this variable? Well, right, we in some sense don't care about those types of details. This is a linear kind of growth rate there. Now, I don't care so much about mentioning the Python stuff right now, but let me just kind of step through it really quickly here. You can actually, right, one of the things we'll mention more in the future, this is kind of a way to use modules in Python, right? So this is kind of a time module. This actually just gives the exact time at a certain point, right? And so what we can do here is if we want to kind of get actual data as far as run time for our algorithm, right? This is not necessarily so consistent always, as we'll probably see in a second, but right, we could define this kind of helper function. We see what time is it now. We run our sum of first n. We output that into the console, and then we say, okay, we now have the ending time, and then we're going to print how long has elapsed. So this is going to be the number of seconds that has elapsed between, right, the start and end. So this is basically going to be timing how long did it take Python to add up this sum of first n things here. And so, right, what we can see then in this case is, right, what is our output here? What kind of is our final thing we're doing? we're exploring this for a couple of different values in this case, right? Well, actually kind of these different powers of 10, right? So we have 1,000, 10,000, etc., up to 1,000,000. So we're exploring the different times we have here. Now, in the future, we'll talk about maybe you want to do averages, right? Especially if we're running this on an online system, some of these times can be a little bit messed up. But so let me just kind of fidget with the results a little bit until we get something that looks kind of decently okay here, right? So first of all, I just want to notice all of these were super fast, right? So this is kind of what I was saying, that code is very, very quick at this point here. And so, right, we have all of our different sum values in this case, right? So we have our first sum here, the time it took for that sum, and this kind of continues along the way up, right? So we have all of these, right? If you know the math behind this, we'll not talk about the math, but we'll see that math in a second in kind of a alternative algorithm, right? But we have the different sums and the different times that it's taking to do those calculations this way, right? Of course, there's some variance, right, depending on things and how big things are, right? Once you get to bigger numbers, those numbers might be harder to deal with, right? So this might be getting kind of slightly slower as n gets kind of big here. But I want to draw our attention at least to the rough pattern, right? That this is kind of growing by a factor of roughly, right, 10 each time, right? So notice here, we can kind of see the growth rate. I guess this is kind of going downward, right? But as we kind of go down in this case, right, it's taking longer. If you just look at those zeros be after the decimal point, right, we have kind of like this growing rate that way. As we kind of change, okay, what's happening as this stuff gets bigger and bigger then. So, right, this is kind of our linear growth rate, right? So we can kind of see and visualize the fact that this is, right, supports this idea of, right, O of n, right, linear growth right here. And like I said, we don't necessarily always want to be calculating these things in terms of running the algorithm, seeing how long it takes, right? That's the whole idea behind the big O notation. But I just wanted to show a little bit here how that kind of works in an example. Now, just to see again, right, what happens if we change stuff slightly here? So let's say here I add some kind of even dummy things into my code, right? So let's say we have here kind of, we want to do 100 times 200, right? So this is kind of dummy step, right? I want to call these kind of dummy steps, meaning, right, they're not doing anything important for our actual algorithm, right? And let's say even I do even something more specific here, right? So for I, or let me say, yeah, I is fine, in range 1 to 100, right? Again, we can do, right, a dummy step here. Right, so if we kind of think about this here, and this is a good kind of example where we need to be careful with our loops a little bit, right? So our first line, again, I don't want to worry about the definition, right? We have one step here. Now note, including this loop only goes from 1 to 100, right? And so actually we don't hit 100 here. So kind of officially this would be 99 steps, right? Now this loop has kind of 2 elements done n times, right? So this is kind of 2 times n in this case, if we want to include the 1 in this case. So now if we added up the steps here, right, let me just kind of label this again. Kind of officially we would have our kind of idea here would be we have 101 plus 2n steps, right? So that is kind of the total number of steps we would have in this case. So now we kind of changed that code. We added these things that don't actually do anything. And I just want to show here that this should allow us to still have a linear growth rate, right? These are kind of changing the things, right? If you didn't actually trust that I ran this, let me just kind of click it a couple more times here, right? So you'll actually kind of see in practice as well, our numbers didn't change that much. We still see a nice linear growth rate as this is going up, right? We are doing more steps here, but the kind of constants don't matter. We want to focus on this O of n in this case. Okay, so that's kind of good in terms of kind of our idea here for O of n. Let's quickly do an example here of, and let me kind of comment all of this out. And I have some stuff down here I want to now uncomment, right? Those of you knowing the math and stuff know we have a nice formula for talking about the sum of the first n, right? So here we have just an equation, right? So we have n times n plus 1 over 2. So this is a perfect example then of this should be, right, O of 1, right? This should be a constant algorithm in this case, right? We're not doing anything kind of particular there, right? We just have kind of our one step at this formula. Again, the details, how does it kind of work that way, right? Doesn't kind of really matter either, right? And if we look at this, all of these times are roughly the same, right? And this is where you have a little bit of variance and kind of probabilistic stuff going on. In fact, supposedly our formula for 100,000 took less than it took for 1,000, right? So this is where you might want to look at averages and stuff, But in this case, we have just a very simple example of, right, constant time. It doesn't depend on the size of that input. Okay, good. So let's head back to our slides now, and let's look at kind of a more complicated example just to practice doing at least one of these kind of calculations for some code here. Again, does this code really do anything in particular? Not really, but we want to just kind of keep that in mind here too as to how long would this stuff take. So a equals 5, b equals 6, c equals 10. These are all single steps. They're not being run multiple times in a loop or anything, right? So we have kind of a 3 right here. So that kind of is just a set 3 in that case, right? Now we have another 1 on the bottom, right? So that kind of is a set single step we have there. Now we have these 2 steps in this loop, and we have these 3 steps in this loop. Now, one of the things you want to kind of be cautioned or careful with, right? The main thing you want to be worried about or think about is loops, right? So loops will often be the most important to analyze and look at in these kind of examples, right? So when you're kind of thinking about these things, look at the loops. Now, in this case, right, both of our loops are kind of from 0 to n minus 1, right? Both sets of loops or whatever have have n steps in the loop. Now, the bottom one is pretty similar to kind of stuff we've seen before, right? So this 2 steps are done n times each, right? 2 steps done n times equals, right, 2n steps in total. So we have kind of for this bottom loop here, we have these kind of 2n steps that we're looking at in this case. Now, the nested loops are a little bit more kind of calculation heavy, or we need to at least pause a little bit longer when we're looking at some of those calculations there, right? So if we're thinking about this loop here, right, what do we really have happening? We have 3 steps done n times, done n times, right? So this is really now where we start to see our quadratic, right? And in terms of loops, oftentimes these things are fairly straightforward to look at, right? So we kind of have n times, that's a square, so we have our quadratic, right? And in terms of loops, oftentimes these things are fairly calculation heavy, or we need to at least pause a little bit longer when we're looking at some of those calculations there, right? So if we're thinking about this loop here, right, what do we really have happening? We have 3 steps done n times, done n times, right? So this is really now where we start to see our quadratic, right? And in terms of loops, oftentimes these things are fairly straightforward to look at, right? So we kind of have n times, that's a square, so we have 3n squared as our kind of number of steps. So the total steps is, right, we have 3 plus 3n squared plus 2n plus 1, so we would have 3n squared plus 2n plus 4. So this would be our total number of steps in this case. And now how do we kind of look at this, right? This would be then O of n squared. We care about this quadratic growth rate for the problem. So this is kind of how a lot of these big O things are going to work. Now, one of the tricky things is not all of the loops are going to be straightforward, right? What if we have a while loop? Then you have to kind of understand what happens. What if you have some breaks in the loop, right? We'll see later on, right? What happens if you kind of have a condition you're checking. If something is true inside the loop, now we're getting out of the loop. So those are making things more complicated. That gets back into ideas from the previous video of best case, worst case, average case, all of those types of things. But we at least want to make sure we have a rough idea how this kind of calculation of the number of steps and how that translates to a big O is kind of done. Okay, now in the kind of last portions of this video, one thing I want to talk about here is some common growth rates. So we talked about kind of some of these already, right? We're kind of also could include linear in here, right? That one just kind of comes up so often, it's kind of maybe not needs to be mentioned right away here, right? But we have constant, logarithmic, right? Log linear, these are kind of things we'll see a little bit later. Quadratic, cubic, right? These are some of the ones I want to talk about a little bit more. And then we get to exponential, factorial, things like that as well. Why do I want to pause here on these kind of quadratic, cubic, you could put linear in there. I want to just mention here, at least quickly, right? All polynomials fit in here. Right, so what do I kind of mean by that, right? I'm not going to explicitly mention degree 4, degree 5, degree 6, degree 100, right? Those are all faster than previous ones, but they all come before any exponentials, right? Of course, for exponentials, we have 2 to the n, 3 to the n, right? All of those exponentials kind of fit in a class there. And kind of factorials would come at the end there as well. And we'll see one example of where factorial comes in a second. But just kind of in general here, if you're talking about investing or something like that, exponential growth is great, right? if we're talking about calculations and runtime and things like that, right? These exponential or factorial rates, right? We try to avoid if we can, right? So these usually are not efficient. Now, that being said, sometimes there's nothing around them, right? So a lot of algorithm analysis is kind of talking about theoretically, can you do this in linear time, quadratic time? Can you do better than linear time? Can you hit log linear or logarithmic, right? And that may or may not be the case. So just like that, maybe it's impossible to do better than exponential. So sometimes your best still might be inefficient, but those kind of growth rates are worth thinking about. And it's almost kind of then a good way to think about ways you could kind of visualize these as well, right? So one of the things we'll kind of look at, this is in your textbook and stuff too, right? But try to look at kind of visualizing these growth rates, right? Or even pull up Desmos or something like that, right? Good to start being comfortable visualizing these growth rates too. And so that's something we'll do kind of in the future too, but that'll be good to try to look at that way as well. So let's quickly look to kind of wrap up this video at one kind of example. So this is in your textbook a little bit more. They have some more explicit Python code, things like that as well. But we want to talk a little bit, and we'll do kind of a little bit of this more, right? You can see the textbook for some more examples of this, but we want to look at ways to check anagrams. So remember, an anagram is just a rearrangement of the letters, right? So if we're talking about kind of different words and stuff, right? So heart and earth, right, are anagrams of each other, right? Because they use the same, right, possibly in a different order, right? So officially speaking here, right, we might want to consider, right, heart and heart anagrams of each other, right? But that's kind of not something that we want to kind of, or that's kind of a trivial thing to think about, right? So these are just kind of that's our goal here with an anagram checking thing. Now, I don't want to look at actual code right here, right? I just want to kind of talk about these ideas quickly to see if even just with the idea, you can come up with the big O notation, right? Or kind of the rough idea of that, right? And so that's the other powerful thing about kind of big O notation. You don't even need to always talk about exact implementations of something, right? Of course, the implementation in code in Python is going to be slightly different than in C or C++ or Java or JavaScript, right? But if you have the general idea of the algorithm, you kind of can just see, okay, it has to be at least this growth rate. It has to be this type of thing. So in terms of these kind of rearrangements, right, and kind of first string matching the second, right, another good thing to think about here is what is kind of our growth rate depending on, right? And so it should be clear here, right? Note n here will be the number of letters, right? If I give you a two-letter word, that should be much more efficient at looking at the different kind of anagrams possible of a two-letter word versus a three-letter word versus a four-letter word, etc. And our first algorithm kind of explicitly mentions that, or kind of explicitly shows that here, right? So what do I mean by examine rearrangements of the first string and kind of to see if it matches the second, right? So the idea here would be like, let's look at a smaller example so I can start doing some kind of easier ones here, right? So let's say we have, right, cat, right? And we want to look and see if this other three-letter word is kind of anagram of cat. So what could we look at, right? We can look at, right, cat. We can look at CTA, right? We can look at kind of ACT. We can look at ATC. And then we have TAC and TCA. Now, if you'll notice what I'm doing here, right? And so I guess maybe this is better on kind of one line here, right? So what we can do is look at all of the rearrangements of the work, right? And so here, right, we have 6 rearrangements. One by one, check if those rearrangements match, right, our work, right? So if we're trying to see if, you know, tac is, right, an anagram of cat, right, then you say, oh, we check them, right? And if you find a match, they're anagrams. If you don't find a match, they're not, right? So we have cat, CTA, ACT, ATC, TAC, TCA, right? Oh, I see TAC there. It is an anagram. I don't see bat there. So bat is not an anagram of cat. Now, right, this here, if you've done some math a little bit, we have 3 letters. 3 times 2 times 1 is 6 rearrangements, right? This is actually, right, of course, a factorial, right? So in general, there will be there will be n factorial rearrangements, right? So this algorithm is probably O of n factorial, right? You're correct. We have to do some work. How are we going to check, right? When we do cat and compare that to tab, you're going to have to say, does C equals T? No, right? You kind of check them letter by letter. There's some extra stuff going on, but remember, as far as big O notation goes, that all is swept away, right? So this kind of first example here would be just O of n factorial. This is kind of our worst case scenario. And in a sense, this tells us why it's the worst case scenario. right? You're kind of looking at all possible rearrangements, and that's giving you our factorial growth rate here. Now, let me just kind of keep our n factorial as the growth rate for this one. So maybe right here, this is kind of, we can label this as O of n factorial. So that is our growth rate for this first expression here. And we now want to do the same thing for our second one as well, right? So check the letters one by one to see if they can be matched up. So we can do kind of a slightly larger example in this case. So, so let's say we want to compare right now. Let's look at, whoops, and okay. So we have our kind of, let's do bats in this case. So how about we look at seeing if we have an anagram, if bats and tabs are anagrams, right? And of course, we could always be doing these things in terms of non-examples, right? Both of the kind of examples I looked at here are actually anagrams, but that's kind of just easier to think about this kind of one by one there, right? So what we could do here, right, is I want to separate, right, go letter by letter, right? So we have a B, right? Then we have an A, then we have a T, then we have an S, right? So we're kind of looking at these letters one by one in this scenario. So we have our 4 letters in bats, and we're going to be kind of looking, for each time, we're going to be looking at tabs, right? So we have tabs then in each of these scenarios. And at least let me here separate my tabs a little bit, so I have some room to work here. And right, the thing I want to go here is, right, I want to make sure we're clear about is that we still need to go kind of letter by letter in this case. So when we look at the B, right, if we look at this line by line, B and T is no, B and A is no, B and B is yes. So what I can do here is cross out the B, right? So let me cross out the B. I know that that one's already matched. So actually this should be crossed out in all of them then. And I just want to point out here, right, I looked at 3 of the letters in that case, right? Or I just kind of went through that list. Maybe even if you want to think about it, right, I went through all of the letters, right? I kind of go through this each time, right? Or conceivably, I could go through all of the letters, right? If I look at the A, right, I'm now going to see the second letter, and then this kind of is 2, right? And then the A is crossed out, the T is crossed out. I looked at 1 letter in that case. And then the last time I look at the letter S, I go through all 4 of the letters, right? And so now at the end, since all letters are crossed out, we have an anagram, right? So this kind of is a kind of example where we now are doing some looping type action here. Now notice here, right, the idea is we kind of go through the first word, right? So we go through n letters of the first word, right? And up to n letters each time in the second, right? So this is kind of where we're getting a double loop. And so hopefully people are kind of starting to see the pattern here that we've done a much better algorithm at this point, right? So we loop through the first word to find the letters, and then for each one of those letters, we have this nested loop for the second set of letters. So here we're getting kind of an O of n squared in this case. Now, some spoilers here a little bit. You can do better than this. So, right, if you want to take a look at this, right, there is some stuff in the textbook. See if you can do better. Try to do better yourself before you look up the answer, right? And that's what we're going to be doing throughout a lot of the time in this course, right? Algorithms will exist, but now we have the tools to say, well, okay, we have the algorithm. Does it work, right? Is it easy to understand? Those kind of are mostly given. And now we want to say, okay, how efficient is it? How long is it going to take to run? What is its big O growth rate? And then can we do better? And so that's what we're always going to be kind of looking at when we're talking about algorithms. Okay, that takes us then to the end of our introduction to big O notation. Right, we're going to be practicing this over and over and over when we're analyzing algorithms. Take a look at your textbook a little bit, right? Practice some of this stuff, right? Even write some silly code yourself. Start seeing how many steps it takes, right? The different growth rates you could come up with. And we're going to kind of be using this more and more in the future as well when we start diving into actual kind of things we want to do in real life, right? I think I mentioned already, but we're going to be starting to do like searching, sorting in the next week. These are 2 of the most important things where we can start really looking at how efficient these algorithms are and comparing different algorithms that way too. So Mr. John here saying thank you for watching the video, and I hope to see you guys in the future as well. Goodbye.